Continuing our discussion of image formation by optical devices, the other major category is the lens. On the screen you see profiles of different shapes of lens, and this is not exhaustive of all the possibilities, but a lens is either of one kind or the other kind, and you can distinguish what kind it is depending upon how the thickness of the lens in the middle compares with the thickness of the lens at the rim. These represent profiles, but a typical lens is actually roughly circular in shape, and if you view it from edge on, you might see one of these six shapes. The lenses that are thicker in the middle, seen from edge on, are called converging lenses. The lenses that are thinner in the middle and thicker at the edges are called diverging lenses. So, what's the difference and how do they lead to the formation of different images? It's important to note that a lens is symmetric in that you can hold a lens up to your eye and look through it, and then you can flip the lens around and you look through it and you're going to see the same thing. That means that a lens has two focal points. A mirror has only one focal point. A lens has two focal points that are symmetric on each side of it. We'll find that with lenses, there may be an image that is real or virtual, upright or inverted, enlarged or reduced. And we'll find that just like with mirrors, we might have to extrapolate rays. But in mirrors, we extrapolated reflected rays. In lenses, we are going to extrapolate refracted rays. To understand the nature of the refracted rays, keep in mind that there is an object that exists on one side of the lens and the observer that exists on the other side of the lens. We see an example here of a concave lens, which is a type of diverging lens. And as you look through the lens, you see the image of the woman holding it, and the image of the woman holding it appears on the other side of the lens relative to the camera taking the picture. The camera is the observer, and the woman is the object. They are on opposite sides of the lens itself. So keep in mind, object on one side, observer on the other. I will represent the observer in these ray diagrams as a small eyeball. So for instance, you see the small eyeball on the far right. You see the profile of the lens, and we're looking at a diverging lens. It's thinner in the middle. And we have our object on the far left. Of course, this object, just like with a mirror, is going to simply be an upright arrow. We see two focal points that are evenly spaced on either side of the lens. Now we start drawing the ray diagrams. And just like with mirrors, we want three rays emanating from the tip of the object. If we can find the location of the image of the tip of the object, then we can assume that the bottom of the object, the base of the object, is on the baseline. You see the baseline, it passes through the two focal points, and it also passes through the very center of the lens. The first ray that we consider is one that passes directly through the center of the lens. Although it's not well represented in the graphic, the assumption is that the lens is extremely thin in the middle. Whether it's a converging lens or diverging lens, we assume that the lens is extremely thin in the middle, so that the ray that passes through the middle is virtually undeflected. And so virtually, we're just going to draw it as a straight line. So you can see the line starting from the tip, it aims towards the center of the lens, and the ray itself continues to the far side along the same path. But now, the ray that exists to the right of the lens is the ray that exists after refraction. And if we want to understand a diverging lens, we're going to have to look at the path of the refracted ray. And the eye is going to assume that the refracted ray originated somewhere along a straight line. So if this red ray were to enter the eye would say, okay, somewhere along this dashed line is the origin, the source of this ray of light. So far, so good, but we need two more rays. And each of the other rays will involve a focal point. One will involve the focal point on the left, the other will involve the focal point on the right. Let's start with the one that deals with the focal point on the left. We start with a ray that is parallel to the baseline until it reaches the lens. Now, you might look at this graphic and you're going to say that ray does not meet the lens. That ray is above the lens. We're not doing an accurate physical depiction of what's going on. We're building a model. And this ray diagram serves adequately as a model. We can approximate the ray as refracting at the instant where it reaches the halfway point of the lens. So this deflection right here is at about the midline of the lens. That's good enough for our approximation. We're looking for a qualitative prediction for the image. Don't stress over literal rays here. So the ray that goes to the upper right is the refracted ray. That's what the eye is observing as it looks at light passing through the lens. And therefore, the eye is going to assume that this refracted ray originated somewhere along the straight line represented by the dashed blue line. Now, this might beg the question, how do I know that this ray has started approaching parallel to the baseline, then refracts away from the baseline? How do I know that's going to happen? Let's look at a close-up of the profile of the lens and a ray as it enters. So here are the two sides, the left and the right side of the lens, represented by the thin curving black lines. And we see the incoming ray represented by the arrow pointing directly to the right. It's going to obey the law of refraction, which is also known as Snell's law. And the incoming ray is in air. The lens is made of glass. Glass has a higher index of refraction than air. And so the light ray is going to bend towards the normal when it refracts into the glass that makes up the lens. But we need to understand what the normal is. The normal is perpendicular to the surface at the location the ray strikes the surface. So we have to be very careful because this surface is curving around. The normal ray is perpendicular at this angle at the location where the incoming ray meets the surface. We see that the incoming angle, the angle between the incoming ray and the dashed normal line, and we see the angle between the outgoing ray and the dashed normal line, and we see that the outgoing ray has refracted towards the normal, just in obeyance of the law of refraction, Snell's law. And so the refracted ray is going to travel through the glass lens along this straight line path here until it encounters the other boundary. And now, the light as it approaches the second boundary is initially in a high index of refraction, and it's approaching a medium with a lower index of refraction. It's going from an index of refraction of glass to an index of refraction of air at this second boundary. Again, we need to determine the normal, but now this time the ray is going to refract away from the normal. We're going from a high index of refraction to a low index of refraction. That means that the outgoing angle is larger than the incoming angle. And the net result is we see that the ray has bent away and above the horizontal. The incoming ray was horizontal. The outgoing ray is above the horizontal. It's bending away from the baseline. So that's how we know. The next ray we draw, the third and final ray for that matter, involves the other focal point. You imagine a ray that starts at the tip of the object and is collinear with a line that connects the tip of the object to the far focal point. And it's going to start on that line until it encounters the lens, at which point in time it's going to refract and it's going to refract parallel to the baseline. So the refracted third ray is parallel to the baseline. The observer's eye is going to say, well, this incoming ray must have originated along a straight line. So now we have our three extrapolated rays as the eye understands them. We have the extrapolated third ray, we have the extrapolated second ray, and we have the extrapolated first ray. And we see that all three of these rays intersect each other just inside the focal point of the diverging lens. There's our image. We see the image is virtual because we had to extrapolate the refracted rays to find them. We see that it's upright, and we see that it's reduced, which is exactly in accordance with the picture that we saw a couple of slides earlier. Oops, there it is. Take a look at the image of the woman as seen through the lens. It is upright, and it is smaller, and it turns out that it is virtual. So the actual ray diagram is in agreement with the actual lens. The ray diagram is serving as a model. It gives us a good prediction. It gives us a perfectly valid prediction for that matter. The diverging lens really has only one case. I can also imagine what would happen if I drew a ray diagram for an object inside the focal point, and there's only some very slight cosmetic changes to the way in which we draw the rays. The first ray is still through the very center. The second ray is going to go parallel to the baseline, but then refract along an angle that is collinear with the focal point on the left side and the point where the horizontal ray meets the midline of the lens. And then the final ray aims for the focal point on the far side, but then refracts parallel to the baseline. These rays are diverging from each other, so we're going to have to extrapolate them backwards. And we see once again the image is still upright, the image is still virtual, the image is still reduced in size. It's a little bit more interesting with the converging lens. The converging lens has two cases, one for when the object is inside the focal point and one for when the object is beyond the focal point relative to the lens. We'll start with the situation where it's beyond the focal point. And again, we're going to assume, despite appearances to the contrary, that the lens is extremely thin, and so that a ray passing through the center of the lens is virtually undeflected. The second ray that we draw will use the focal point on the left side. Imagine a line collinear with the tip of the object and the focal point on the left side. We draw a ray emanating from the tip of the object collinear with this line to the lens, and then that line refracts parallel to the baseline. And then the final ray deals with the focal point on the right-hand side. Now, you might have noticed that the light refracts towards the baseline. So we saw that the incoming ray of light was getting farther and farther away from the baseline until it impacted the lens, and the lens brought it more towards the baseline. That's why it's called a converging lens. And again, we obey Snell's law. We obey the law of refraction. The normal at the surface, the refracted ray is going to be closer to the normal than the incoming ray after the first surface, but after the second surface, the refracted ray is going to be at a greater angle than the incoming ray because we're going from a higher index of refraction to a lower index of refraction. Now, the second ray, as I said, is going to involve the focal point on the the final ray is going to involve the focal point on the far side. We start off parallel to the baseline, and then we refract directly through that focal point. And our three rays, put together into the same ray diagram, give us a result in which the rays do intersect each other. And we see that the image is formed through actual rays of light, so it's a real image. We see that the image is inverted, and the image winds up being a little bit reduced in size. Now, in your life, you might have held a magnifying glass. A magnifying glass is a converging lens. If you've ever held a magnifying glass at arm's length and looked through it at a distant object, so you're holding the lens pretty far away from you, the distant object that's seen through the lens is going to appear inverted. Now, if you're using the magnifying lens and holding it up close to your eyes while you're looking at a distant object, that's like having your eyeball in this ray diagram right next to the lens. And so the rays are just going to be all kind of fuzzy with each other. But if you hold the magnifying glass at arm's length from you and you look through it at a distant object, you'll see that the image that's created is inverted. And if you focus on it, you'll realize that that image is actually pretty close to you. It's on the same side of the lens as you are. Here's a conceptual question to kind of test whether you're understanding this idea. We have a beam of light that's sent through an aquarium. We also, in the aquarium, we have a lens. We happen to have an identical copy of the lens outside of the aquarium, and when the beam of light shines through it, we see the light passes through the lens like so and creates the pattern you see up above. Where the light focuses together is the location of the focal point. If I have this same lens in water, now the index of refraction of a lens is greater than the index of refraction of air. The index of refraction of a lens is going to be greater than the index of refraction of water. But the index of refraction of water is greater than the index of refraction of air. What effect is this going to have on the shape of the beam as it exits the lens? In particular, where will these beams find a focal point? Will that focal point be closer to the lens? Will it be at the same position from the lens? Or will it be farther away from the lens compared to the situation outside the water seen at the top of the graphic? Think about it. Let me know if you have questions. The second case for the converging lens, the object is inside the focal point. Now, this is the classic magnifying glass situation. And if you've ever used a magnifying glass, you should already know that the image is going to be larger than the object. Let's see the ray diagram predict this. The first ray passes through the center of the thin lens, undeflected virtually. The second ray, we use the focal point on the near side. We imagine a line connecting the focal point to the tip of the object, and then the ray that is emitted by the tip of the object that is collinear with that line, we move it towards the lens, and then when it reaches the midline of the lens, it's going to refract and be parallel to the baseline. The third and final ray is going to start off parallel to the baseline. When it reaches the midline of the lens, it's going to refract and pass through the focal point on the other side. The refracted blue, the refracted yellow, and the refracted red rays are diverging from each other. There's no way they're going to intersect. So we have to extrapolate them backwards. And we see that their extrapolations backwards gives us an intersection. And that tells us the location of the image. We see that the image is upright. Well, if you've ever used a magnifying glass, you see that the image is in the same orientation as the object. We see that the image is larger. Well, if you've ever used a magnifying glass, the image is larger. That's why it's called a magnifying glass. But it is virtual. It's not a real image. We don't have actual rays of light passing through it. So that's the difference between a magnifying glass used to read and a magnifying glass like in this situation where we have actual rays of light. You can focus sunlight onto a point And if you were a strange little kid like I was, you would start burning holes in your G.I. Joe doll. But perhaps I've said too much. If we want to quantify things, the nice thing is we have exactly the same equations for the mirror, except for the business with the focal length. In the case of lenses, while there's a lens maker's formula some of you may have heard about, the focal length of a lens will either be given or it will be a goal of the problem to solve for it. The symbols that we use for the lens variations of the equations are the same as with the mirrors. P is the object distance, P will be positive. Q is the image distance, Q can be positive or negative. The focal length will be represented by a lowercase f, and the magnification will be represented by a lowercase m. But now we have to apply our sign conventions correctly. A diverging lens, which is sometimes referred to as a concave lens, has a negative focal length. A converging lens, which is sometimes referred to as a convex lens, has a positive focal length. So be careful about the uses of the words concave and convex, because a concave mirror is a converging mirror. A concave lens is a diverging lens. A convex mirror is a diverging mirror. A convex lens is a converging lens. Crazy, but be careful. As for the image distance, it is positive when the image is real and the location is on the opposite side of the lens relative to the object. If Q is negative, that means the image is virtual and on the same side of the lens as the object. Otherwise, the major equations are the same. 1 over F equals 1 over P plus 1 over Q, and N equals minus Q over P. And you can also say the height of the image equals N times the height of the object. Let's take a look at an equation. We want to know the focal length of a lens with the following values. We have an object that is 4.75 centimeters tall, and it creates a 2.91 centimeter tall image. The image is upright. This height is created when the object is 27.3 centimeters away from the lens. Okay, let's start dissecting this. We have an image that is upright. Well, the diverging lens creates an upright image, but the converging lens can create an upright image. So we haven't been able yet to distinguish whether we have a converging lens or a diverging lens. But if it's a converging lens, the virtual image, the upright image, will be larger than the object. If it is a diverging lens, the image is smaller than the object. Well, based on the numbers we're given, the image is smaller than the object. We have a diverging lens. The fact that we have a diverging lens means that the focal length f is inherently a negative quantity, and the image distance q will be a negative quantity because the image in this circumstance appears on the same side as the object. Just check the ray diagram. What's the magnification? Well, we know it's upright, so it's going to be positive. So we take the image height and divide it by the object height, 2.91 divided by 4.75, and we get a magnification of positive 0.6126. This allows us to express the image distance in terms of the object distance. M equals minus Q over P. Therefore, Q is equal to minus M times P, minus the magnification times the object distance. The object distance is always positive, so we're going to do negative 0.6126 times positive 27.3. We get negative 16.72. The image distance is negative as we predicted. Finally, we can solve for the focal length. 1 over f equals 1 over q plus 1 over t. Q is equal to negative 16.72, so we have 1 over negative 16.72 plus 1 over 27.3 equals negative 0.02316. Don't forget to take the inverse of that number. The focal length is 1 over negative 0.02316, and we calculate the focal length to be negative 43.2. Our prediction was that it was a diverging lens, and that we should expect the focal length to be negative. The math bears that out. Everything is consistent with each other, so have some pretty good confidence in this solution. I hope this is going well. Take care. Bye-bye.